If you've ever tried to explain something really, really complex, you know that words alone just don't cut it.
Right. It's like trying to describe a jet engine over the phone. You need a diagram. You
Right.
need a blueprint.
Exactly. And that's the challenge in massive software systems. So for today's deep dive, we're looking at the solution to that problem, the Unified Modeling Language, or UML, and a framework for organizing it called the 4+1 architectural views.
And this is so important because you can't just hand someone a million lines of code and say, here, understand this. You need a common visual language so architects, developers, even clients can all get on the same page.
So what we've synthesized from our sources today is really a master key. It's about how this combination gives you a shortcut, a set of tailored blueprints, so that everyone involved gets the exact view they need.
The whole mission here is clarity. We're giving you the tools to visually conceptualize systems that would otherwise be just, a black box. For you, the learner, this is like gaining instant fluency in professional software documentation. It just cuts through all the noise.
Okay, let's unpack that, starting with the language itself, UML. We've said it's a visual language, but why is that so critical for what we call object-oriented design, or ODE?
Well, it's a great question. The whole point of ODE is organizing code around objects, and more importantly, the relationships between those objects. And those relationships can get incredibly complex.
Too complex for just text.
Way too complex. Text just fails. UML is that specific, standardized visual grammar built to explain classes, their components, and how they all talk to each other. It's the alphabet for our blueprints.
So if UML is the alphabet, what's the biggest practical win you get when a team actually uses it fluently?
It's immediate intuitive communication. I mean, think about a new developer joining the team.
Right.
Instead of making them read 500 pages of specs, you show them a few UML diagrams, boxes and arrows, and they can instantly grasp the core parts of the system and how they connect. It just eliminates so much ambiguity.
Okay, but here's where it gets a little tricky in the real world.
Yeah.
If UML is this perfect foundational document, where does it sometimes break down?
It breaks down with change. If you're using a traditional waterfall model where you design everything up front, document it perfectly, and then build it, UML is fantastic.
But almost no one does that anymore.
Exactly. Most teams now are agile or iterative. Designs and requirements can shift every 2 weeks. And in that environment, trying to keep a massive set of detailed UML diagrams perfectly up to date becomes, well, it's a huge chore. They can become outdated the moment the code changes.
That's a crucial point. The documentation is only as good as it is current. So we have the language, UML. But even with a great language, you still need structure, right? You can't just have a folder with 100 random diagrams.
And that's the perfect transition. We move from the language, UML, to the structural framework, the 4+1 views. It's basically a highly organized way to present a collection of UML diagrams, ensuring we cover 5 essential perspectives.
But isn't that just adding more complexity? 5 views instead of 1. Why not just have one giant master diagram for everything?
Because different people care about completely different things. The end user cares about features, the programmer cares about code organization, the system engineer, they care about server loads and network traffic.
So you're tailoring the view to the stakeholder.
Precisely. This framework creates high-level views specifically for those audiences. It makes sure the client isn't getting lost in deployment details, and the engineer isn't wading through marketing copy.
It's like organizing the library of blueprints by department. Okay, let's break them down. Let's start with what you call the core, the logical view.
The logical view is the system's anatomy. It's the static heart of object-oriented design. It focuses purely on the what. What are the data entities, what are their attributes, and how are they related?
So in a banking app, the logical view would show you an account object, a customer object, and the line connecting them. For you as an end user, this view directly translates to the features you actually see and use.
Exactly. It's static, it's conceptual, but once you have the anatomy, you need the physiology. How does the system actually run? And that brings us to the second view, the process view.
The process view. So this is the how. It's all about runtime behavior.
Yes, this is a dynamic view. It's crucial for system engineers. It tackles the really hard problems in modern software, things like concurrency, performance, scalability.
Give us a concrete example.
Okay, imagine a ticketing website. A huge concert goes on sale. Suddenly, you have 5 million users hitting the site at once.
Yeah, crash and burn scenario.
Right. The process view is the document the engineer looks at. It shows how that load is distributed across servers and threads so the whole thing doesn't fall over. The logical view says the roads exist. The process view shows how the cars flow without colliding.
That makes perfect sense. Okay, different perspective now. The person actually building the roads.
Yeah.
Let's talk about the development view.
Right, sometimes called the implementation view. This is the programmer's blueprint. If the logical view is the design of a car engine, the development view is the actual list of parts and the instruction manual for assembling it.
So it's about managing the code itself.
Strictly software management. It shows how software components relate and, how all the thousands of class files are gathered into modules and packages. It's about keeping the code base organized so the team can work efficiently.
It stops developers from tripping over each other's work. Okay, next up, we hit the real world with the physical view.
This one shifts away from code entirely and focuses on deployment. It's the system engineer's perspective on the actual hardware, the physical servers, the networks, how the software components are installed across that whole topology.
Now, our sources had a really practical point here. It said that if your application follows a really common pattern, like a standard cloud architecture,
Then you might not even need a super detailed diagram.
right, you can save a lot of time.
Absolutely. If it's a standard setup, you don't need to reinvent the wheel. But if you have a complex, non-standard system, maybe with special hardware like IoT sensors, then this diagram is absolutely essential for the operations team.
Okay, so we have four. The logical, what it is, the process, how it runs, development, how it's built, and physical, where it lives. That brings us to the plus one, the context view.
The context view is the grand narrative that ties it all together. Some people call it the use case view or the scenarios view. It describes the system's boundary and how it interacts with the outside world.
I think scenarios view is really helpful because it focuses on the actors that use the system.
It does. It defines the scope, who or what is interacting with your software. And it's not just human users. It crucially includes any automated external interfaces. Think of a third-party data feed or an API your system has to respond to. The context view frames that entire interaction.
So with those five views, you get this complete multifaceted picture of the architecture. But, seeing these diagrams in a book is one thing. How are people actually generating them today?
Yeah, nobody wants to draw these by hand anymore, especially not in an agile environment. That's where tooling comes in, and the one our sources highlight again and again is a tool called plantUML.
plantUML. So this is an open source tool that does the heavy lifting for you. You don't drag and drop boxes, you just write a simple text file describing the diagram.
And the tool renders it for you. This is a huge workflow improvement. Remember our agile problem. If a class relationship changes, the developer just changes one line of text, and the diagram is instantly regenerated. It keeps the documentation in sync with the code.
And it's incredibly versatile. I mean, the textbook authors we looked at used it for every single diagram, from simple class relationships to really complex sequence diagrams.
And there are basically two main ways people use it. The first, and probably most popular for developers, is right inside their code editor, like VS Code.
Right. You install an extension, and you can see a live preview of the diagram right next to your text description as you type. You just have to configure it to use a renderer, which can be remote or local.
We don't need to get into the specific extension names or server URLs here. That's all stuff we can put in the show notes for you. But the core idea is that the software automates that whole translation from simple text to a clean visual diagram.
And the second method, for the power users.
That's setting it up to run locally from your command line from the terminal. This gives you total control. To do that, you need a couple of things installed on your system first.
Okay.
You absolutely need the Java runtime environment, and you also need a library called GraphViz. GraphViz is the engine that actually figures out the layout of the boxes and lines.
And once that's set up, you can just run a command, and it automatically creates the image file for you. It's all about making generation so efficient that you actually keep your diagrams updated.
So we've really come full circle. We went from this abstract need for a common language all the way to the concrete tools you can use to generate the diagrams that provide it.
And that really is the bottom line here, isn't it? UML provides the visual clarity, and the 4+1 model makes sure you're looking at the architecture through all the right lenses, function, process, deployment, and management.
And for you, the learner, knowing these 4+1 views is a professional shortcut. The next time you join a big project, you know the 5 core documents to ask for. It lets you get your head around the complexity of any new system so much faster.
Absolutely. And if we go back for a moment to that context view, the +1, it describes every external entity, human or automated, as an actor that the system has to respond to.
Which leads to a really interesting final thought. When we design a new system, do we fully consider how the needs of the automated actors, say, a high-frequency trading API that needs microsecond responses, might conflict with the needs of the human users who just want a simple, intuitive interface. And in the final design, do we implicitly end up prioritizing one type of vector over the other? Something for you to mull over.